Hi, and welcome back. Let's say, or let's do this example on ionization energy. And let's just say I gave you a collection of different ionization energies. So I said that for the first ionization energy, so IE1, or this is going to be the energy required to remove the first electron from the atom, or to make a 1 plus cation from whatever atom we're dealing with. To remove that first electron, our ionization energy is going to be 578 kilojoules per mole of whatever atom that we've got. So in order to remove, I guess, a mole of electrons from a mole of a certain atom, we have to put in 578 kilojoules, I should say. IE1 equals 578 kilojoules. That's how much energy we would have to put into the system to remove the first electron from this atom. Then we've got our second ionization energy. So IE2, where this is going to be the ionization energy required to remove the second electron. So this ionization energy is going to be 1820 kilojoules per mole. So this is going to mean that if we wanted to figure out the energy to remove two electrons, we would have to add these two numbers together, right? So this is the energy required to remove that second electron after we've removed the first one. So this is ionization energy 1 to remove the first electron, ionization energy 2 to remove the second. So then after that we've got ionization energy IE3, and that is going to be equal to 2,750 kilojoules per mole. And you can see as we go up it gets harder and harder to remove that electron. And then finally we've got the fourth ionization energy, so IE4, and that is going to be equal to 11,600 kilojoules per mole. And what we are supposed to try to figure out is which third period element, so I'll write that in, which third period element, so we're talking about elements in this period, so it could be any of these elements. Which of these elements has got this ionization energy configuration? And hopefully you could see, or hopefully just a little bit talking about, I guess I should talk about what exactly it is that we're looking for. What we're really concerned with when we're looking for this ionization energy is this big jump, right, between ionization energy 3 and ionization energy 4, because all of these other ones you can see that they're not as big a jump as we have here. We saw a jump of almost 10,000 kilojoules per mole. That's way more than any of these other successive jumps. Like, we could see that it kept on getting harder and harder to remove an electron, but between the third electron and the fourth electron, it got really, really hard. It got really, really hard to remove that fourth electron. So which element do you think this is? So let's just say, let's think about this. And I'm trying to think of the best way to show you which element it is. But if you can imagine, which ionization energy is this going to correspond to? Which ionization energy is this atom really, really not going to want to do? That we're going to have to put all of this energy into the system to get it to do? Well, it's going to be when it loses that noble gas electron configuration, right? It's when it loses that full valence shell of electrons, where it has 8 valence electrons, right? So this ionization energy, when we go from losing 3 electrons. So we've already lost 3 electrons. So we could think that once we lose 3 electrons, we're at a nice, happy, stable place. But then once we lose the 4th electron, we're much, much less stable. We're much less happy. So you can think that this 4th period is when we went from having a noble gas-like electron configuration, or a neon-like configuration, to having a fluorine-like configuration. So instead of having 8 valence electrons, we now have 7 valence electrons. So this is going to be our 4th ionization energy. So you can think that going into the neon stage was our 3rd, and then going from, it's kind of hard to write the 3rd. Let me see if I can write there. I'll just say that arrow is going to be our third ionization energy. And then this arrow, where we go from magnesium to sodium, that's going to be our 2nd ionization energy. And then this one, it'll be a nice long arrow from aluminum to magnesium. That is going to be our 1st ionization energy. So this means that the element that we are looking for that has the ionization energy of this configuration in the 3rd period is going to be aluminum. And you can think about it this way. Aluminum has got 3 valence electrons. So it loses the first one, and and even though aluminum, you could say it wants to lose 3 electrons. That's the easiest way for it to get to a noble gas electron configuration. It wants to lose those 3 electrons, but we still have to put energy into the system to get it to actually do that. So it loses its 1st electron, and we didn't have to put in that much energy. It loses its 2nd electron. We had to put in a little bit more. It loses its 3rd electron. We had to put in even a little bit more than that. So now we've got, after it loses its 3rd electron, it has its noble gas electron configuration. And then it loses another one, and we have to put in a way more energy into the system to get it to lose that final electron. So anyway, aluminum is the element that we're looking for. So aluminum. That's the element in the 3rd period that would have an ionization energy configuration somewhat like this. So anyway, hopefully you found that useful, and I'll see you in a future video.